let's start the second talk. Thank you very much for coming. We have Błażej from University of Warsaw, and he will be talking about Langevin Monte Carlo, beyond Lipschitz.
Yes, so basically I will talk in opposite direction than Gareth talks previously because I will start from diffusion and construct algorithm deterministic. So it is opposite way. This talk is joint work with Maciej, Iwona, Jorgen, and I am really grateful for Adam to allow us to do this project because he has 9 months and he do not accept all projects. On some projects he allows us to work, on some he does not allow us. But how this topic came, the people, Iwona and Jorgen are the people from the PDU community, and we try to discretize non-local Fokker-Planck equation. And if we use the techniques which we used before to analyze unadjusted Langevin algorithm, we end up that it requires Lipschitz gradient continuity, which in the PDE community is quite strange assumption if we will assume that potential are just quadratic, not super quadratic. So in this paper about discretization of PDEs, we have found the way how to solve this issue. And then we immediately found that this issue can be solved for Langevin Monte Carlo. So this is the story how this team was constructed and why we get this interest on the beyond Lipschitz gradient continuity case. So, but we have very traditional problem. We would like just to approximate diffusion up to normalizing constant. We have some potential V, and this V it will play a central role in the talk. So x of minus V is our target distribution. We are not very interested in the unbiased algorithm. We can allow some small bias. We would like to control just how good is approximation in terms of some distances. It could be biased or not. So we start as traditional Langevin Monte Carlo, just with Langevin diffusion. So it is very standard way. And if we take very standard Euler-Mariaman discretization, or call it Langevin Monte Carlo, or call it unadjusted Langevin algorithm, this is very standard way of thinking about constructing Monte Carlo algorithm. And this algorithm is, we know almost anything about this algorithm, almost everything. This algorithm is studied, I think, many years. But what is known? Basically, almost all papers consider global Lipschitz continuity of gradient. And usually we use some convexity assumption or just some Lox-Sobolev inequality that measures these phi's. But almost all it is global Lipschitz. Sometimes people consider Helder continuity of gradient. And there is a lot of results which bounds convergence in terms of Kullback-Leiber divergence or in Wasserstein distance. These results are usually explicit in dependence on dimension. So basically, the people are interested on the how the convergence depends on dimension. And usually we get polynomial rate of divergence of the dependence on dimension, and what kind of theory are used to prove such results. So first, which is very natural way, it is just because it is discretization of diffusion process. We can think about let's take the results of convergence of diffusions and couple it with some comparison with discretization. So it is the first way of thinking how we can analyze Langevin Monte Carlo. And second way of thinking is that it is quite a new way of thinking is that Fokker-Planck equation can be described as a gradient flow of Wasserstein distance on the space of Wasserstein distance. And if it is gradient flow, then we have just a problem of minimization some functional. And if we minimize functional, so we can think that we don't compare with diffusion, but with optimization procedure in the space of measures. So, and this gives some different tools of analyzing, but basically results of these two approaches are quite comparable in some sense. Okay, so this is what we have and what we know, and I just put some not full list of papers about Langevin Monte Carlo from last 6 years. I choose 6 years because then my paper is also covering in this range of time. This is a very natural way of thinking about time. But this is, as you see, there is a lot of papers considering the theoretical properties of Langevin Monte Carlo. So, and basically, most of this paper just, or a lot of paper just try to relax convexity assumptions. So this is or Poincaré inequality or log Sobolev. But that's I would like to say that this is a lot of attention. Okay, so go back for a moment to what means these assumptions. And if you write just gradient Lipschitz continuity says that our potential is upper bounded by a quadratic function. Convexity means that we are lower bounded by linear function. If we assume strong convexity, then our target is just trapped from below and above by quadratic functions. So it seems to be not very comfortable situation. So it is quite limited distributions. And okay, so we really don't want to think about this lower bounds. We would like to say why we need this upper bound. And can we relax this assumption in any reasonable sense? So this was our goal. So if we relax this assumption, so we will consider distributions with lighter tails than quadratic. So this is our goal. And what happened? So basically, it looks as that if we take Euler-Mariano discretization, we have no chance to derive any algorithm outside Lipschitz continuity, because it is well known that this Euler-Mariano discretization is transient outside without this assumption. So it is well known why it is transient, and to understand why it is transient, we can go back just to optimization procedure on the Euclidean space. Just consider gradient flow of potential V and say what happened. We could have two Euler schemes, explicit and implicit. Euler-Mariano discretization use explicit Euler scheme inside. And if we have explicit Euler scheme, so it is very nice because we can just perform this Euler scheme. Implicit is not very nice because we compute the gradient at the endpoint of our scheme. So we need to solve such equation to get implicit Euler scheme. What is nice, what I will show you soon. Okay, if we have explicit Euler scheme, the algorithm is monotonic not only, but if gradient of potential is Lipschitz. Otherwise, the step after explicit Euler scheme could grow the potential V arbitrarily large. Could be arbitrarily large after potential V. So this is basically the reason why it makes a problem. Implicit Euler scheme keeps, by the definition which I will show you later, that we have the monotonicity of this Euler scheme, even if if V is not convex. So let's see how it works. So first, I just make a picture of very simple potential. I believe that this is x to the power 4 or x to the power 6. I don't remember exactly. And I will start here, and I will do just 2 steps of explicit Euler scheme with properly chosen step size. So first step is not look very bad, but it is the value of V slightly increase. I do next step, and the value of V increase twice more. If I will do another steps, I will end up somewhere, maybe somewhere there. Next step of this Euler scheme. So this is the way why Euler-Marmot discretization explodes and becomes transient. And what happened if I take implicit step? So the first step from here, we really decrease function. And another step, instead of going here, we go toward the minimizer. So it seems that it is known that implicit Euler scheme is much more stable than explicit. So the idea is to use implicit scheme inside discretization, and we hope that this will help to get a reasonable algorithm. Okay, so how to get implicit Euler scheme? And implicit Euler scheme is closely related to proximal operator. The proximal operator is defined like this optimization problem. So we try to optimize value of potential, but with adding penalty if we go too fast. Just writing the optimality criteria for this problem, we see that proximal is really implicit Euler scheme. Just realize implicit Euler scheme. So the proximal steps is what we need to incorporate in our algorithm. By the very definition, we have monotonicity. Yes, because if we take x, we get here just v of x, and we definitely we need to have v smaller because other part is positive. So really, we don't need anything to assume about v. Expect that proximal operator is well defined to get monotonicity of potential. The issue is that it is a really limited number of examples where we can give explicit formula for proximal. It looks bad, but it's not very, very bad because at least if we assume that V is convex, this minimization problem is not difficult to solve, at least numerically. So our idea is to, do the steps with proximal steps, but not perfect proximal step, but with some error which is produced by some numerical routine insight to implement in the implementation. So this is our idea. So next it is to explain this idea from a different perspective, not from the stability of discretizations, but from the perspective of gradient flows. So it is so what means that Langevin diffusion is a gradient flow in Wasserstein space? It means basically that it could be translated that our target distribution is minimizer of a functional. This functional is quite easy. This is just potential energy and entropy. So we have we have composite of two functions to minimize, functionals to minimize. So another idea is how we can think about Langevin Monte Carlo is that we split this functional to the two functionals. In the first step, we try to optimize this part, and in the second step, we try to optimize this part. So let's take a look. What is the gradient flows of this both part of the functional? And it's again we see. So if we will just do perfect algorithm, the splitting algorithm, but in one step we optimize the first part of a functional, in the second step, second part of a functional, we end up exactly in the case that the gradient flow of this functional of energy is exactly push forward of proximal operator. This is explicit formula for this gradient flow. And second thing is what is also known that gradient flow of entropy is a Brownian motion, so it is just adding Gaussian noise. So this is so basically if we do proximal steps instead of gradient step in the algorithm in Euler, we perform explicit gradient flow of energy in the first step. So we don't incorporate any error on the first step. What is also nice if we, because gradient flows of these both functionals are geodesically convex, so gradient flows is contractive. So if we introduce error, this error will not propagate too much by this contractive property. So this suggests that if we compute proximal step not explicitly with some error additional, nothing wrong nothing very bad should happen. So this is the idea which ends with our with algorithm which we called inexact proximal Langevin algorithm. So this algorithm is just this strange notation is due to the theoretical part that we have 3 sub-steps. In practice, we have just 2 steps. First step is we try to compute proximal step starting from xk, but we allow to have some error, and this error, this error is bounded by delta. This delta will be used forward in theoretical analysis. So we need to run any routine which approximately compute proximal step. Second step is just traditional step of adding Gaussian noise, and this is the whole algorithm. So this is just formulation of algorithm. So what we know. So okay. So just to follow further formulation, we divide this step to 3 sub-steps. First step is just true proximal step. Second step is artificially that we have some additional noise of proximal step. And the last step is adding Gaussian. So this is on the, if we write this formulate on the terms of random variables, we have such a formulation. If we go to the formulation on the cities, the first step is a push forward of proximal operator. Second is a convolution with this additional error of computing proximal. And the last is a convolution with a Gaussian measure. And so this is all what we need from this slide. Okay. So now what kind of assumption we need to have in our analysis? So okay. So to basically okay. First assumption we just say that the potential is convex. Second assumption just is not very it's not very bad. It is just saying that in the tails we have tails which grows faster than quadratic, or at least quadratic. We formulate this in that this is strongly convex in the tails outside some given ball, with lambda strong convexity constant lambda v. The third assumption is only technical assumption, just to simplify formulation. We can all formula will be awful if we do not assume that the minimizer is at 0. This is not really assumption. This is just simplification of the statements. And the last assumption, okay, we need something to control the growth. So how we need to control the growth? The growth we need to control that the growth of a function is polynomial. And basically, okay, this assumption could be translated just that function v is locally Lipschitz with polynomial growth. This is what we know, and we know the important thing is this qv is the rate of the growth of in the tails of the function v. So we don't allow any growth, we allow any polynomial growth. And instead of Lipschitz constant, we have local Lipschitz constant somewhere hidden in this formulation. This formulation it can be obtained from the local Lipschitz assumption and polynomial growth by some generalization of descent lemma, which is traditionally from Lipschitz we have here quadratic bounds. This is exactly the same way. Okay, so what is the cost of having this? We need to pay some cost. We need to assume that initial measure when we start has qv plus 1 moments finite. And basically, this is quite a natural assumption, even if we go back to the formulation of diffusion process, because under such assumption, the diffusion solution to Langevin diffusion exists if we assume that initial measure is has some even higher moment that QVW plus 1 you need to have existence of diffusion process. I don't remember exactly, but you need higher moments of initial measure to have existence of solution of SDE even. So this is, but in context of Monte Carlo, this is not any dangerous assumption because we arbitrarily choose our initial distribution, so it is our choice. It has to reduce our choice on the of initial measure. Okay, let's go. So what is our main result? So our main result is that if we okay, first we need to our assumptions. We need to restrict our step size, but step size is smaller than 1 over this strong convexity constant in the tails. And if epsilon is, if tau epsilon is small enough, alpha states that delta is comparable to tau 1 plus alpha. So delta should be smaller, of smaller order than tau. Delta, it is just the error of a computing proximal step. And if delta is, if we just take the delta of order 1 to the tau square, then this is about this tau epsilon is of order epsilon, and it's quite natural. So, but under such assumption, we have boundary of Kullback-Lieberg divergence between output of algorithm and true distribution of order precision with precision epsilon. It translates to the complexity such that if alpha is larger than 1, so if we take that delta is of smaller order by 1 of step size, then a complexity of algorithm is the dimension to this power, which depends on the QV, sorry, and epsilon to -2. And it reduced to the basically optimal results for Langevin Monte Carlo when QV is equal 1. So QV equal 1 means that the exactly gradient Lipschitz continuity. So this result naturally extends the best known results for gradient Lipschitz case. If we allow bigger error of proximal operator, we lose something in the dependence on the precision. Complexity of precision will be worse. So we can slightly improve this results when we assume that strongly convex, so that the potential is strongly convex everywhere, not only in the tails. So in this case, basically, we have then precision in Wasserstein distance, and complexity is also the same order, and also it agree with the best known for gradient Lipschitz case if QV is equal 1. So it seems that this is very natural extension of these results. And here we can allow bigger error of proximal steps because here we just need this alpha larger than half. So it gives slightly better, but it is not surprising that this difference between why it is not surprising, because if we are in the strongly convex case, then this functional from this variational formulation gives functional which is strongly convex, and then we have strong contraction of gradient flow. So this error not only not accumulate, but the error is vanishing with time, introduced error. So this is the reason why we have better rate here. Okay, so this is our main results. So now I will try to show you how we prove it, basically. How we prove it. So this is the paper about discretization of non-local Fokker-Planck equation, from which we have ideas. So basically, under our assumptions, with the same notation which is presented before, if we have splitting algorithm, we need to control three things. How good is previous slide? Yes. Oh, kappa. It is some constant which relates between delta and tau. It is. It is just to precise write the constant. This kappa. Basically, here it is saying that delta should be of this is of order 1 tau. So the error of proximal step should be of lower order than step size.
Something found plays the role of like a condition number that you would expect in
This.
So you've got that part.
This one. This lambda v.
This is kind of the strong convexity part.
Yes, this is so. If you think about Lipschitz constant, so if the potential is C2, then Lipschitz constant is the highest eigenvalue, and the lambda v is the smallest eigenvalue.
So where's the bit that kind of penalizes? Is there a bit? So there's nothing in the bound that penalizes for anything growing particularly fast or anything like integers of step size.
No. Yes. Okay. So if we would like to analyze the splitting algorithm, we basically need to know how good is the algorithm in the convergence of the first functional and the second functional, and also what is the loss in terms of the first functional if we do the steps for the second part. So so if we do this says what happened with FV if we add Gaussian noise. So this is the loss of this accuracy after splitting, and and only here we see the issue which comes from non-Lipschitz gradient. It means that here we have some moment of a measure of order QV minus 1. So this is the cost. So we need to control this moment to make this finite. These two parts are rather standard, so it is basically what we expect from the optimization algorithm in convex situation. So this is the difference, and of course, we need slightly more because we don't have only two steps. We have another steps. We have these steps which says that we have incorporate additional error in the proximal step. So we also need to control these two guys. These three lemmas are very standard just from the convex optimization. And additional lemmas says that, okay, what happened with the energy FV if we produce additional error in the proximal step. And this says, and again, this is some issue because here there is some constants. This is of order delta, basically, but the constants depends on the now QV moments of distributions. So to apply these lemmas in our case, basically we need to control this moment of algorithm. So this is the place where again where our main technical difficulties related to the non-gradient Lipschitz case. In non-gradient Lipschitz here, we need only to control second moment. Here we need to control higher moments. So this was quite painful part of proving to get bounds on these moments, which are independent on the step size and with nice dependence on dimension. So this is the part. To finish the proof, basically we need these moments. Okay, so what we are able to get is that there exists some constant which depends on the moment, such that all moments are bounded in such a way that it is dependent on this constant is to power minus m and the dimension m to m over 2. So this is the theorem which help us to get the bounds, and additionally, if we have such relation between error of a proximal step and step size, then that this constant behaves well in some sense, that they do not explode in the way what we don't want to explode. Because unfortunately, this constant also depends on lambda v, but this dependence is that if lambda v is going worse, so going to 0, this constant is stabilized. So this is not dangerous dependence. This constant could explode if lambda v explodes, but this is not the case what we are interested in. Okay. So how to prove this result? So to prove this result, we need basically two first inequality. Just to this inequality comes from the assumption about strong convexity in the tails. Basically, it's not surprising that if you are strong convex in the tails, we can find some constant that this step of adding of making proximal step will not increase the moment, but even decrease. So this is the convergence of like. Next, basically, we need to compute the moment for the second for m equal 2. And it is just a straightforward computation. Basically, this is the same proof as for the second moment in the case of gradient Lipschitz case. So it is very standard place. And next, but we need to for all m. So first way is to get all moments below 2. But this is very easy. We just apply Jensen inequality, and Jensen inequality gives us exactly what we want. So we are in the position that we have all moments up to 2, and later we will use induction arguments. We'll use induction arguments, and basically the main part is such inequality, and this inequality is just Taylor expansion of function x to the power m. It is just Taylor expansion with some formula for reminder. This C is just this. Why it's nice? Because then we have basically what we expect, that we have this term, which will be by this inequality we will have contraction, and here we have lower order moments, which by induction assumption are bounded. So we have exactly the same structure for all moments that we are able to bounce everything using induction assumption. So basically all details of these proofs are available on the archive paper about numerical methods. So this is the key proof of for moments. And then basically, if we have finite moments, we really derive a very natural, very common classical inequality in the convex optimization, that the functional one step is bounded by the difference of the Wasserstein distance plus some constants. And to finish the proof, we just need to summing this inequality, use Jensen inequality on the left-hand side to get what we need, some average measure, and that's all. That's really all. All difficulties were hidden in the moment bounds. So this is a very classical way. So okay, so we get proofs, we get algorithms, and so the rest of the talk I will try to convince you that this algorithm works in practice. Yes, because what is dangerous is first how it works really, and second it is this. One could ask, it is really hard to compute a proximal step in practice. And in our simulations, we have only the loss of time by factor 5. So the computing in exact proximal steps cost 5 times more than computing gradient step in use Langevin Monte Carlo. So we believe that due to strong convexity of a problem where you compute a proximal operator, the cost should be of logarithmic of the precision, something like that. Some additional cost should be logarithmic term. but we don't prove it precisely. So we start with very simple example, just the distribution with light tails. And we compare three algorithms. We compare our algorithm, it is inexact proximal Langevin algorithm, with tamed Euler and Euler. And what happened? If we consider this algorithm, and if we start at the center of the space, we consider the problem on dimension 1000. Dimension 1000 to really consider a high dimensional situation, and to see that it is difficulty to compute it. But basically, it's not difficulty. So here, if we start in the center, all algorithm works. Okay, what are these two things? This is a relative error and coefficient of variance. Coefficient of variance is just standard deviation divided by mean. Just to we compute it just to have because this value, if you compare second, 4, and 6 moment, the values are completely different magnitude. So to see what kind of type of error we have, so we compute relative error and coefficient of variance. So first of all, if we start in the center of a space, nothing wrong happened with tamed Euler, and nothing really wrong happened with Euler, but we get better relative error for second moment, comparable to fourth moment, and slightly worse for sixth moment. But we do not observe nothing wrong from for Euler if we start in the zero. Maybe we do not have enough time to run to see if the process is transient. But if we start in the tail, what means in the tail? I think we start at the point 4 or 5 on all coordinates, something like that. Then Euler immediately explodes, and we don't have any result. Really, any results? It really explodes, and our algorithm works, and it behaves it's twice better than tamed Euler. So this is just the numbers. What happens? So let's see. Just a trace plot of the first coordinate of a process. So after just 2 steps, we observe that Euler explodes after some very large numbers, and we don't see the trajectory further. Basically, I think one more step. It could be observable, and next it goes for the place where the potential gives not a number in the Python just. So it's after a few steps, and tamed Euler converges to the center, and blue one is our IPLA, which converges faster. If we just forget about Euler, we see what happened. Using proximal steps, we really fast go back from the tails to the center. Why it is natural? Because if we do implicit discretization of gradient, then still the size of a step is unbounded. We can do large steps because we use gradient at the end point, but not bounded. If we use tamed Euler, the gradient is size of a step is bounded by 1. So we need to wait long time when with tamed Euler go back to the center of the space. This is the why tamed Euler is not very efficient in this problem. Next question was okay, how these 2 algorithms are robust to the choice of the step size. And we see that tamed Euler is much more robust and it requires smaller steps than our algorithm to work. Yes, if the step size is smaller than our algorithm, of course, it's better, but it is much more the area where the error is small is much larger. So it is less sensitive for choosing the step size, at least in this example. And the last question was how behavior of our algorithm depends on the error of proximal steps. it was quite challenging to perform this simulation because on the beginning we saw that any of implemented numerical procedure converged in 2-3 steps to the correct values. So we cannot use real numerical methods. So finally we say, okay, let's do the perfect proximal steps and add auxiliary noise. Just add auxiliary error and see what happened. So this error is exactly of this rate because we compute perfectly proximal step and add error after computing. And we see that if error is lower of the step size, basically nothing changes. Nothing changes. This is just Monte Carlo error because we just by limited number of replication. So this is nothing happening. And if numerical error becomes larger than the step size, then it becomes to growth and it starts to accumulate. So it looks slightly better than in our theoretical results because our theoretical results says that that the numerical error should be of lower order than step size. Here we have that it could be of the same order, but it's not very surprising. So it's confirmed that we don't see very big relative error even if we do big error in the numerical approximation of proximal in comparison to the step size. Okay, so the second model which we would like to analyze is just more complicated. So this is a Ginzburg-Landau model. So there are some parameters, and this is also a fourth order model with some some interaction parts which are not non-trivial. And for this, there is no proximal explicit proximal formula for proximal steps. Explicit formula. This model was considered, I don't know, in your paper, will you consider? Yes, you consider this model. Okay. And again, we compare 3 algorithms. And again, what the conclusions are very similar from the numerical schemes. If we start from our algorithm works, doesn't matter if we start in the tails or in the center of the space. EULA explodes when we start in tails and behaves quite stable if we start in the center. And our algorithm is mostly twice better than trained EULA. This dimensionality was not very high because it was the strange problem. We are not able to tune well Hamiltonian Monte Carlo to compute reference value of true expectation moments for higher dimension. I don't know why. It was impossible, so it was not high dimensional. But in this case, our algorithm, it could be really efficiently implemented in high dimensional settings also. So it was not an issue. And the last thing, it is just this example does not satisfy our conditions. It is Bayesian image deconvolution, where so to deconvolve we add prior distribution of the image, which is total variation norm. And the posterior distribution should denoise the picture. We present this, we compute this example just to check that in the case where the potential is really hard to compute proximal, does it affect time of computing of our algorithm? And in this case, the result was, the cost was 5 times larger than for EULA, just. So it's not, so this is still, so this is what was done. We take a picture of who was in Warsaw, know this building. This is our Palace of Culture. This is the picture after adding noise. Oh, sorry, it is opposite. This is original, this is after adding noise, and this is by the Bayesian image deconvolution, so by posterior distribution sampling by our algorithm, what happened. So this is this is basically all what I'd like to say about methodological part. I have 2 slides about advertisements. So first, advertisements is that I am co-organizing of a thematic research program in the Warsaw about evolutionary PDEs, but there is also will be workshop about diffusion in Warsaw, and on this workshop we try to invite people, both community from the some statistical and machine learning community who applies diffusion in the research, and researchers from PDE. And we believe that such a connection could be useful for both community. So this is, I invite you to join this workshop also, because this is, we try to build some bridges between communities. And the second invitation is for the people who ask me, does this will be MCMC workshop in Warsaw? Yes, it will be in next year, not in Warsaw, but in Eindhoven, and we will organize it with yours. So that's all what I'd like to say.
Have time for some questions.
Yes.
Yeah, I think very interesting. So, can you do this stuff for partially implicit methods?
I believe yes, but I really don't know how to do. I don't think about it yet. So
Because I mean, partially implicit methods that if you do things in the right way, you can inherit the best advantages of fully implicit.
yes. I believe that it could be done, but I have no idea how exactly to attack
guess
it.
I presume that if you do that, you can get some modification of your proximal.
Yes.
That thing which
I know that there are some algorithms which use midpoint between explicit and implicit, and this algorithm has slightly better convergence rate. Yes.
You think the bias is really much worse with the dimension when this Q is big? Because I can see how it would come from the proofs, but qualitatively it would seem quite strange.
But the bias?
Yeah, as in, you know, or the complexity bound, say, when you have a big QV, it gets much worse. Right?
Yes.
Qualitatively, I would expect a different story.
I see what you mean. You believe that basically the measure concentrates is more better concentrates, so it is easier to explore. But on the other hand, I think that in this case you really you can be really wrong in the estimation of tails, because you will not really rarely go to the tails. So my intuition is not very obvious. Is it true or not?
So if you measured in not KL, but in transport, it would be more likely to be true. But in this setting, it seems okay.
I don't know. I think that the bias could be better, but I don't see any way of proving it with using the moment bounds. So
I mean, my intuition was that you say you do the proximal steps
yes.
exactly, then you say that's an LMC on the envelope, and then I just do triangle inequality. It won't work for the KL.
But if you can take we have results for just explicit proximal steps in the case of a PDA paper, and basically we have the same dependence on dimension of error. So it's not maybe the more natural thing what you can think you can get, but we have no idea how to do it better. Yes, but so my intuition is not really, you know, that you have better, you are more concentrated in the center, but it could be the impact of the error in the tails is bigger also.
Kind of the way you wrote the problem that, you know, say you have the problem where the potential is x squared plus some constant times x to the 4.
Yes.
Then it depends on the constant which behavior you're going to get. It's a bit related to what Sam was asking before, that somehow the condition number will be, is the tail behavior dominant or subdominant? No.
Yes.
It will play a meaningful role.
Yes.
not something that's been studied very well.
So I see your intuition. And I have no idea how to prove it.
Another big question, I guess, is that, you know, when we're in this case where you have the strong convexity, the normal thing you get is the log Sobolev inequality for the measure, right? But when you have this faster growth in the tails, you have these even stronger things, like
Yes.
ultra contractivity and so on. And it would be interesting to see that come up in the analysis somehow. But
Hmm.
again, maybe there's too many things fighting each other.
Well, maybe, yeah, the strong convexity just help us that when you use gradient flow theory that this is really contractive. Maybe we're too lazy to solve that. Even if you have just strong convexity in the tail, you have also strong contractivity of this flow.
Yeah, it's kind of for the different method, like what they have in the.
Yes, yes, but probably we were too lazy to get better results.
One final. Okay, let's thank the speaker again.